Welcome back to the deep dive. If you work in the world of information security, compliance, or architecture, you definitely know that the complexity of your controls. It's kind of meaningless if you haven't first figured out the basics. So today, we are doing a deep exploration of those basics. Asset security.
And this isn't just theory, right? For anyone who tracks the Certified Information Systems Security Professional Certification, the CISSP, or deep diving into Domain 2.
Right.
And while it historically accounts for around 10% of the exam questions, the concepts here, they're the very bedrock of any functional security program.
That's why our mission today is so critical. We're providing you with really a complete roadmap for protecting anything that holds value to an organization.
Yep.
That journey starts with identification, moves through the asset's entire life cycle, and then concludes with the necessary technical controls, things like state-based encryption and obfuscation.
And we absolutely must emphasize the stakes here. Asset security is where theoretical risk meets, well, painful real-world consequences. Our sources continuously stress that a single minor vulnerability, maybe an asset that was misclassified, or an employee who wasn't properly assigned a role, that one thing can expose an entire system.
We're talking catastrophic failure.
Catastrophic. Loss of funding, regulatory penalties, data exposure.
What?
It can compromise a company's entire reputation and, honestly, its viability.
Okay, so let's unpack this fundamental challenge, because the sources describe asset security as, and I'm quoting, easy to understand but hard to implement. When the core concept is just protect your stuff. Why is implementation such a beast, especially for, large, complex organizations?
Well, the dichotomy comes down to scale and resource allocation. In theory, sure, protect your stuff.
Right.
But in a global enterprise, your stuff is 5 million digital assets, millions of lines of source code, intellectual property, physical servers, client data, employee records.
Yeah.
And they're all governed by different geographical laws, different retention mandates, different owners. It's a mess.
So the goal is massive. We have to understand data management, longevity, addressing everything from creation to end of life, or EOL, end of support,
Yes, yep.
and then determining the appropriate security control for each stage of each asset.
Precisely. And look, if you are a CISO, you don't have an infinite security budget.
Not at all.
So if you apply, say, bank vault security to every single document, from the CEO's salary report all the way down to the office catering menu, you waste incredible amounts of money and time.
And you create friction.
Worse, you introduce so much friction that people inevitably find insecure workarounds just to get their jobs done.
That is the classic resource optimization problem, isn't it?
Yeah.
If you treat all data as equally important, you pretty much guarantee two things. You overprotect the non-critical data, and you inadvertently underprotect the truly vital assets.
That's it. So the key takeaway before we even look at controls is this.
Oh.
You must first understand an asset's significance before you can protect it effectively. Asset security is fundamentally about prioritizing risk.
Which brings us directly to the foundational step, asset classification. This is the cornerstone of all that priority setting.
It really is asset classification. It's the systematic process of assigning assets the level of protection they require based directly on their value to the organization.
Okay, that seems intuitive.
It seems intuitive, but in a security context, it's a strict principle. The protection you apply must align directly with the asset's determined value. You cannot put a six-figure control mechanism on an asset that only has, say, $50,000 in potential loss value.
And crucially, the security team itself.
Yeah.
They aren't generally the ultimate authority on defining that value, are they?
No, they're not.
That responsibility lies outside the technical sphere.
It does, and this is a major point of confusion for new security professionals, the owners of the asset. They're always in the best position to understand the actual business impact and regulatory risk that asset represents. This makes their input, their risk acceptance, their definition of criticality absolutely crucial to the entire classification process. The security team provides the frameworks and the mechanism.
And the owner defines the value.
The owner defines the value and the risk acceptance.
So the owner might say, this customer list, this is worth $10 million in revenue, and then the security team comes back and says, understood, that classification level requires this specific type of encryption and these access controls.
Exactly. Without that value assignment from the owner, the security team is just operating blind. They're guessing at priority. This is why tools, procedures, and robust training are so essential to make classification effective across the whole organization.
Okay, let's nail down a conceptual nugget here.
Mm-hmm.
The subtle but really important distinction between classification and categorization.
Yes.
These terms are sometimes used interchangeably in the broader business world, but in a security or compliance context, they are very distinct.
Very distinct. Classification by itself is the system of classes an organization sets up based on policy.
So, the big picture.
The big picture. Think of this as the organizational framework for sensitivity. Public, internal use only, confidential, secret, top secret. These are the fixed, high-level protection levels defined by a formal policy document. It is the schema.
And categorization is the operational verb.
That's a great way to put it. Categorization is the act of assigning one of those classification levels from the defined system to a specific asset. So you might categorize the executive salary database as secret.
And the company lunch menu as public.
Exactly. The goal is that, ideally, every single asset should be categorized into a classification system so they can be protected based on their determined value.
Right, so classification is the predefined framework. Categorization is the act of fitting an asset into that framework.
Yep, and that separation allows the framework to stay stable even as new assets are constantly being created and categorized.
Okay, so once an asset is categorized, it needs identification standards applied. And here we run into another pair of terms, labeling and marking.
Right, and these are often confused because they seem to do the same thing.
Sure.
Define the data, but they serve fundamentally different masters.
Okay.
Labeling refers to the asset's classification, and it is specifically designed to be system readable.
How did that manifest in practice? What does that look like?
Well, this is metadata. We're talking tags, file attributes, database fields, things that automated systems like data loss prevention DLP tools or access control mechanisms can read instantly.
So a system sees the label.
Right. A DLP tool sees a label that says confidential, and it automatically blocks that file from being attached to an external email, regardless of where it's stored.
And marking. That's for the meat space.
Oh.
For the humans interacting with the asset.
Precisely. Marking refers to the handling instructions and is fundamentally human readable. This is the footer on a printed document that says proprietary, return to security if found.
Or sticker on a hard drive.
Yeah. Or a color-coded sticker on a physical hard drive, or a watermark on a secure presentation slide. Both labeling and marking must be consistently applied across all organizational assets, but the labeling that does the heavy lifting for the automated controls.
Now, I know the source notes that security professionals are often tested on the cost-effectiveness considerations of different labeling approaches. This moves beyond just the theory of classification and into, well, budget realities.
It is entirely about budget versus risk tolerance. Automated labeling, those system-readable tags, it's highly effective and scalable. It provides robust protection and consistent enforcement. But setting up the scanning, the indexing, the policy enforcement across a global infrastructure is extremely expensive and complex. It requires specialized tooling and a lot of maintenance.
So if you have low-value or low-risk data, you likely shouldn't be investing millions in automated labeling for it.
Exactly. For low-risk assets, manual marking, the human-readable element, is significantly cheaper. It just requires policy enforcement and training.
But the downside is pretty obvious.
The downside is that human compliance is notoriously inconsistent. People forget, they get lazy, or they deliberately ignore the instructions. So a security professional has to determine the optimal mix: robust, automatic labeling, and technical enforcement for the high-value assets.
And then simpler, cost-effective marking and strong auditing for the lower-risk assets.
The protection level must always, always justify the cost of the control mechanism.
Moving from abstract classification to actual operational protection, we have to define handling requirements. This is where policy meets the physical world.
This is Domain 2.2. And the core logic is simple. The higher the classification of the asset, the greater the controls needed to restrict who can handle it, where it can be stored, and how it must be disposed of.
And this is where we need to emphasize a critical distinction again. The handling requirements are based exclusively on the classification of the asset.
Yes.
Not the type of media it lives on.
This point is absolutely vital. A file classified secret requires specific security controls, physical access restriction, logging of all views, enforced encryption, audited destruction, and it requires that regardless of whether that file is printed on paper, stored on a high-availability server cluster, or copied onto an encrypted thumb drive. The physical medium doesn't downgrade the asset's sensitivity.
Interesting.
The classification dictates the required protective environment for that medium, whatever it is.
So the custodian can't say, well, it's only on a cheap USB stick, so it doesn't need high-level physical security.
No way.
If the data on it is secret, the physical stick has to be secured as though it were the entire server rack.
Precisely. And that prevents the classic mistake of focusing security only on the central storage infrastructure, while completely ignoring the proliferation of highly sensitive data onto endpoints and portable media.
Once handling standards are established,
Mhm.
we have to define who is responsible for enforcing them. This is secure provisioning, and it begins and ends with clear roles and accountability.
Accountability is the engine that drives security policy. I mean, if everyone is responsible, no one is responsible.
Right.
So the classification process must identify the owners as they are ultimately accountable for the asset. If security fails, we need a clear chain of ownership, which is why our source material details 5 critical data roles.
Okay, let's break these down meticulously, starting with the data owner or controller.
This is the executive or manager who interacts with the asset the most. They're the one who signed off on the initial risk assessment. They are ultimately accountable for the asset's protection and its regulatory compliance.
They make the big decisions.
They make the high-level policy decisions, what classification level is needed, who has general access, what the retention period should be. They own the budget for the data and the risk of its loss.
Okay, next up is the data processor. This role has gained major significance with global regulations like GDPR.
Absolutely. The data processor is responsible for processing data on behalf of the owner or controller.
So a third party.
Often, yeah. It's an external third-party cloud service or maybe a specific internal department like payroll. The key point is that the processor is acting under the instruction of the owner-controller. They're responsible for the security of their operations, but the ultimate accountability still rests with the owner.
Got it. Then we have the technical implementer, the data custodian.
The custodian holds the technical responsibility for the data. They're the ones who implement the controls and configurations defined by the owner.
So the IT folks.
They're the database administrators, the system engineers, the IT operations teams, yes. They are responsible for the custody of the systems and databases, running backups, applying patches, managing physical and logical access controls. The owner defines what to protect. The custodian determines the technical how.
Okay, so if the data is breached because the encryption key was stored incorrectly, the custodian is likely responsible for the failure to implement policy correctly.
Probably, yes.
But if the data was breached because the owner classified it too low in the first place, the owner is accountable.
That is an excellent summary of that risk division. Now, let's look at the data steward. This is the role that's most often overlooked or confused with the custodian.
The steward handles the business side of the data, is that right?
That's correct. The data steward holds the business responsibility for the data itself. They focus on data quality, definition, and use. They make sure the data is accurate, properly formatted, and used consistently across the organization.
Can you give an example?
Sure. They would ensure that customer ID means the same thing in the sales database as it does in the financial ledger. This role is crucial for data governance and maintaining data integrity, which is a core security tenet.
And finally, the data subject.
The data subject is simply the individual to whom personal data pertains, the person being described by the data. This role is fundamental when we're discussing privacy and compliance, especially with modern regulations that grant individuals specific rights over their information.
Like the right to be forgotten.
The right to be forgotten, the right to access their data, things like that.
So if we synthesize this whole chain, why is distinguishing these 5 roles so crucial for a robust security architecture?
It prevents ownership gaps and provides clarity, total clarity for incident response and legal proceedings. In a breach scenario, you instantly know who was accountable for the decision, the owner, who implemented the failed control, the custodian, and who defined the data structure that might have been compromised, the steward. Without these clear lines, risk acceptance is fuzzy, policies get ignored, and ultimately accountability just dissolves in a complex enterprise structure.
And all these definitions, the roles, the classification levels, the handling standards, they all have to be formalized in the data classification policy. So what is the overarching purpose of this document?
The policy's purpose is to manage information lifecycle governance. It's there to ensure that all sensitive and valuable information is protected and handled correctly throughout its entire existence. It's the formal blueprint for the whole asset security domain.
And what considerations are the biggest drivers when you're drafting this policy? What do you have to think about?
Well, the policy is really a reflection of the organization's risk profile, so it has to consider a wide range of factors. First and foremost, laws and regulations.
GDPR.
Well, APA,
Right.
all of those. Then privacy requirements and specific customer requirements like contractual mandates. Internally, it must account for the cost of creation of the data, the operational impact of losing it.
Right. If the manufacturing blueprint is lost, production just stops.
Production stops. And then, of course, resulting liability and reputation damage. The policy has to be comprehensive, and it has to bind those legal requirements with technical implementation standards.
Let's follow the data itself as it moves through its entire life. Once it's created, classified, assigned an owner, it enters the data lifecycle. And that covers everything from active use to disposal.
This is Domain 2.4, and the principle here is absolute. Proper controls must be in place from the moment of creation and maintained throughout the entire lifecycle. It's a continuous security obligation.
So you can't have any gaps.
No gaps. Data must be protected at each stage, whether it's being input, being stored, being processed, being shared, or being destroyed. The moment protection lapses at any point in that cycle, the asset is vulnerable.
Okay, so the end of the life cycle data destruction. This presents maybe the single greatest challenge to data confidentiality. We're talking about the lurking issue of data remanence.
Data remanence is a terrifying concept for a security professional
Why is that?
because it's the physical evidence that data existed on a medium even after you've run standard dilution procedures. If you simply format a disk or hit delete, you're just removing the file pointers. The underlying data bits often remain, and they're recoverable with common forensic tools.
So the industry focus has completely shifted away from simple removal and toward this modern, rigorous standard of defensible destruction.
Defensible destruction is the crucial goal. It's the organizational process that lets you confidently prove that there is no possible way for any person, even a highly determined individual with advanced laboratory equipment, to recover the destroyed data.
It requires proof.
It demands documented, verifiable procedures, and it's what security professionals must aim for to manage risk.
And the source material highlights three critical concepts related to destruction that we need to master. First up, the categories of sanitization.
Right. These are the recognized tiers of protection. Starting from the lowest effort, you have clearing, which involves overwriting data multiple times to make it unreadable by normal software. Then there's purging, which is a much more intense process, often magnetic degaussing or specific cryptographic functions, that renders data unrecoverable even with advanced lab techniques.
And then the ultimate step,
And finally, there's physical destruction, which is the gold standard.
which naturally leads to the second point. What is the most effective or secure method of sanitization?
If confidentiality is your absolute priority, the most effective method is almost always physical destruction. I mean, we're talking shredding, pulverizing, incineration, or using a certified process like degaussing for magnetic media.
If it doesn't exist, it can't be recovered.
If the media physically ceases to exist or is rendered unusable by data storage standards, the data cannot be recovered. However, this has to be balanced against cost and operational practicality. You don't burn a high-value SAN array every time you retire a few terabytes of data.
Of course not.
Yeah.
And finally, a very modern challenge. The best method for dealing with data remanence in the cloud. You don't own the physical disk, you can't physically destroy it.
This is the operational trade-off that has basically birthed a new standard, cryptographic erasure.
Okay, how does that work?
Since you're relying on the cloud provider to handle the physical destruction of the underlying media when it's retired, the most reliable and immediate method you control is key management. You encrypt the data using your own strong keys, and then when the data is ready for destruction, you just destroy the keys.
So the data is still there, but it's useless.
Exactly. Even if the underlying data remnants persist on the cloud provider's physical media, without the key, they are permanently indecipherable ciphertext. You've achieved defensible destruction under your own control.
That's a genius operational solution. Eliminating the key is a definitive action that is far easier, faster, and more auditable than trying to eliminate the electrons on a disk you don't physically possess.
Exactly.
Now, destruction isn't always the end. Sometimes the law or business continuity demands preservation. This brings us to 2.5, ensuring appropriate asset retention and archiving.
Data archiving is a non-optional part of the asset lifecycle for most industries. It requires specific controls for protection, even though the data is retired from active use.
And what drives that?
Critically, this process is driven entirely by a formal retention policy. You don't archive data just because. You archive it because you have a legal, regulatory, or business reason to keep it for a specific duration.
What are the primary factors that determine those retention requirements?
The three major forces are legal requirements, regulatory mandates, and industry standards. Think of the Sarbanes-Oxley Act, SOX requiring financial records retention for certain periods, or HIPAA mandates for patient records.
And business needs too.
Of course. Beyond law, business needs might require keeping design documents indefinitely for intellectual property protection or archival records for auditing historical business decisions.
When data moves into an archive, it often moves onto cheap, slower media, tape libraries, deep cold storage in the cloud. What are the necessary elements of data archiving policies we have to consider to maintain security?
We have to maintain the full CIA triad, even in retirement. The policy needs to stipulate robust confidentiality controls, strong encryption, rigid access control to the archive location. It needs to ensure integrity.
How do you do that over decades?
Periodic hashing checks, digital signatures, ensuring the data hasn't suffered bit rot or tampering over decades, and critically, availability, meaning redundancy, secure physical or geographic location, and a guaranteed method for restoration, even if the technology to read the archive changes in the future. Archival security is about planning for decades of static protection.
Okay, now we get to the granular controls. We've identified, classified, and planned for the asset's entire life. The protection we apply now has to adapt to the data's specific condition at any given moment.
This is 2.6, and it's critical. Data exists in one of three states at any given time: at rest, in transit, or in use.
Okay.
The security controls that protect data can be completely different depending on which state the data is in, making understanding these distinctions paramount for selecting the right technical control.
Let's start with data at rest stored on a disk, a server, or in a database. What is the primary focus of security here?
Protection for data at rest is centered on two things: preventing unauthorized access and maintaining confidentiality if the physical media is compromised.
What are the methods?
Methods include things like volume or full disk encryption, FDE, file level or database level encryption, robust role-based access control or RBAC, and ensuring comprehensive encrypted backup and restoration strategies.
And the source material highlights a specific concern regarding confidentiality during cloud migration. The question is, how do you protect the confidentiality of data being migrated to the cloud?
Right, and while migration does involve the transit state, the best way to guarantee confidentiality is to secure it before it ever moves.
So, encrypt on-prem.
The standard best practice is encrypt the data using your own keys before it leaves your on-premises environment and ensure it remains encrypted at the cloud destination. This process, often called client-side encryption, ensures that the cloud provider never sees the data in plain text, even during the movement phase.
Okay, next state. Data in transit, or data in motion. This is data moving across networks, whether internal or the public internet. This introduces complexity, especially when comparing transport encryption methods. We need to clearly delineate between end-to-end encryption and link encryption.
This distinction is crucial for network architects. With end-to-end encryption, or E2E, the data portion of the packet is encrypted immediately upon transmission from the source node. And it remains encrypted through every single node until it reaches the final destination node. Intermediary routers or proxies only see the external routing information.
So only the sender and the ultimate receiver can decrypt the payload. What about link encryption?
Linked encryption operates on a segment-by-segment basis. Here, the packet header and the data are encrypted between each node.
Well, everything is encrypted.
Everything is, but the critical difference is that the header and data are decrypted at each intermediary node.
Oh.
Meaning the plain text content is available at every router or proxy server along the path, just long enough for the node to read the header, re-encrypt it, and send it on the next link.
That seems inherently less secure for content confidentiality. I mean, if an attacker compromises just one of those intermediate nodes, they get the plain text.
They do.
Why would a secure organization ever choose link encryption over end-to-end?
That's an excellent challenge. The trade-off is header protection. Link encryption encrypts the packet header. This hides the routing information of the packets traversing a network. providing significant protection against traffic analysis by external observers.
Ah, so they can't see who is talking to whom.
Right. If your primary threat model is a third party watching your network traffic patterns to determine who you are talking to, link encryption is superior for anonymity. But if your primary concern is the content, E2E is always the choice, even though it exposes the header information.
So content versus metadata analysis, a core security design decision. Then we move to the ultimate stealth solution, the onion network.
The onion network, which was popularized by systems like Tor, is a highly effective method for data in transit that solves many of these problems simultaneously. It uses multiple layers of encryption, routing the traffic through several relays like the layers of an onion,
Right.
where each relay only knows the identity of the node immediately before it and the node immediately after it.
And the key insight here is that it provides a double layer of defense against sophisticated surveillance.
Absolutely. An onion network provides both strong confidentiality of the data and anonymity of the participants. It makes it exceptionally difficult to determine the sender, the receiver, or the actual content while the data is moving. It's the gold standard when both traffic analysis protection and payload protection are paramount.
Okay, final state. Data in use. This is the security nightmare. This is data actively residing in computational memory RAM, cache, or being actively processed by the CPU. Traditional encryption fails here because the data has to be decrypted to be processed.
Exactly. The memory state is highly volatile and exposed. We rely on three major strategies here. First, robust controls like role-based access control to ensure only authorized individuals can even access the computing environment.
Look.
Second, digital rights protection and data loss prevention to monitor and block exfiltration in real time.
And third, the fascinating, though still often academic, concept of homomorphic encryption.
Homomorphic encryption is often cited as the future solution to data in use because it allows computations to be run on encrypted data without ever decrypting it.
How did that even work?
Imagine you want to find the average salary of your employees. You could encrypt all the salary data, send it to an external processor. That processor runs the calculation on the ciphertext and returns an encrypted result.
And you decrypt just the final answer.
You decrypt the result and you get the average, but the processor never saw a single plaintext salary figure.
That sounds revolutionary. What are the practical constraints? Why aren't we doing this everywhere?
Currently, it's complexity and performance. Homomorphic encryption is computationally expensive. It significantly slows down processing speeds. Also, it's not suitable for every type of computation yet. It works well for simple arithmetic, comparisons, aggregated statistics.
But not complex transactions.
Applying it to highly complex transactional operations is still a massive challenge. For now, systems rely on secure enclaves and strong RBAC, but homomorphic encryption is the ultimate goal.
Moving beyond encryption, security professionals rely on obfuscation. Now, the goal here isn't necessarily cryptographic protection, but rather hiding or replacing sensitive information to make it obscure, unclear, or unintelligible, usually for a non-production environment.
Right.
So why choose obfuscation over full encryption in, say, a development test bed?
The key distinction is usability for testing. You need data that is realistic enough in format, type, and size to ensure your application performs correctly, but it cannot be the actual production data.
Got it.
Obfuscation techniques allow developers to maintain the look and feel of sensitive data fields while completely eliminating the risk of a breach from the test environment.
Okay, let's break down the 5 specific methods detailed in the source and give a practical example for each, starting with concealing data.
Concealing data is the simplest form. It completely removes access to the sensitive data attribute. So if a field, say, an employee's exact date of birth, isn't needed for a test case, the column is simply suppressed or omitted entirely from the test dataset. You're just concealing it from the test environment.
Okay. Next, information pruning, or pruning data.
This is commonly used in non-production environments. It involves removing sensitive parts of the data from specific attributes. For example, pruning the middle 6 digits of a credit card number, leaving only the first 4 and the last 4.
So the format is still valid for testing.
It's enough for the application to validate that the format is correct, but the actual card number is secure.
Then we have fabricating data.
This is data generation. It involves creating entirely fake synthetic data to replace the real sensitive data. If you have millions of customer records, you generate millions of realistic-looking but completely non-existent usernames, addresses, and account numbers.
And the dataset still works.
It maintains the statistical profile and referential integrity of the real data without containing a single sensitive piece of real information.
And trimming data. How does trimming differ from pruning?
Trimming removes a part of an attribute's value specifically for identification purposes. Think of a long, unique identifier. If you only need to know the first 3 characters to determine the region, you trim everything else off.
So it's about length.
Generally, yeah. Pruning usually deals with removing sensitive middle portions, like a credit card number. Trimming deals with removing the less significant tail end of a long value, typically used when only a segment is needed for a specific test validation.
Okay, finally, encrypting data as an obfuscation method.
This involves creating ciphertext of a value done at the attribute, table, or database level. Within the context of obfuscation, it's often done using a simpler non-production encryption scheme.
And the keys are handled differently.
Right, often the keys are kept securely only within the test environment. This ensures that even though the data is technically encrypted, its primary purpose is to satisfy the compliance requirement that the data is unusable in the non-production environment without authorization.
To finish our discussion on controls, let's look at 2 major security systems that enforce these policies: digital rights management and data loss prevention, starting with digital rights management, or DRM.
DRM is specifically focused on protecting intellectual property IP assets and the rights of asset owners. Its purpose is focused entirely on limiting the usage, modification, or sharing of copyrighted content, software, digital media, blueprints, things like that.
And the legal foundation in the U.S. is the Digital Millennium Copyright Act, the DMCA. This implies a powerful blend of legal and technical enforcement.
It does. Security awareness has to account for DRM techniques because they're often the last technical line of defense against IP theft.
What are the key technical techniques used in DRM that security professionals need to understand?
First, licensing agreements that are baked into the technology that restrict access, for example, only 5 installs permitted. Second, the use of strong encryption to render the content unreadable without the proper decryption key, which is often tied to a specific hardware identifier. Third, embedding digital tags or watermarks that tie the content to specific license holders, allowing easy auditing or tracing of leaks.
And finally?
And fourth, the use of related technologies that actively restrict actions, such as preventing screen capture, disabling printing functions, or blocking the copying of files.
Finally, data loss prevention, or DLP. This mechanism seems to be the one that pulls together all 3 data states we talked about earlier.
DLP is the active enforcement arm of your classification policy. Its focus is identifying, monitoring, and protecting sensitive data in real time. And DLP systems are explicitly designed to protect data in all 3 states: data in use, data in motion, and data at rest.
How does the mechanism work across these 3 states?
DLP tools employ pattern matching and contextual analysis to detect and prevent breaches. For data in motion, a DLP tool monitors email and network traffic, blocking transmission if it detects, say, a high volume of credit card numbers or classified labels attempting to leave the internal network.
And for data at rest?
For data at rest, it scans file shares and databases for unencrypted files containing defined sensitive identifiers like social security numbers, and it triggers an alert or mandatory encryption.
And data in use?
For data in use, it monitors endpoints. It can block unauthorized actions like printing a sensitive report or copying a database table from a terminal window.
So DLP is the real-time, active enforcement mechanism, making sure the classification and handling policies are obeyed across the entire life cycle and landscape.
Exactly. It's the constant surveillance and prevention layer that ties the classification framework to the technical reality of data flows and employee behavior.
This has been a deep dive into asset security, covering the organizational policies and technical controls essential for protection. We moved from the high-level policy of classification all the way to the technical nuance of transport encryption. If we synthesize the journey, identify, classify, handle, provision roles, lifecycle, retention, and controls, what is the core theme for the practicing security professional?
The core theme is risk-based resource application. A good security professional protects assets by knowing exactly what they have, classifying it rigorously based on business value, and applying controls that are appropriate for that value and the data's state and sensitivity. The goal is defensible, auditable protection that is also cost-effective.
Let's revisit the most essential conceptual nuggets for the listener, the distinctions that truly make the difference in architectural design and policy creation.
First, you have to solidify the distinction between classification, the system or framework defined by policy, and categorization, which is the act of assigning a level to an asset.
Got it.
Second, truly understand the separation of accountability. The data owner accepts the risk and defines the policy. The data custodian executes the technical protection. That's the difference between governance and implementation.
Right.
Third, master the encryption differences for data in transit. Understand why link encryption is useful for traffic anonymity, but sacrifices confidentiality at intermediary nodes, unlike end-to-end encryption. And finally, recognize that modern data disruption is defined by defensibility, the ability to prove non-recoverability, which often means cryptographic erasure in the cloud.
It is all about creating a system of accountability that is documented, testable, and enforceable for every single piece of information that holds value.
The security job never ends until that asset is verifiably destroyed.
Which brings us to our final provocative thought for you to mull over. We discussed how retention policies are often driven by laws and compliance, sometimes requiring high-value data like financial records or IP ownership papers to be held for indefinite periods or decades. We also established that the security goal for retired media is defensible destruction, the ability to prove eradication.
So here's the contradiction. If sensitive data is governed by legal holds that essentially mandate infinite archival protection, does the concept of defensible destruction ever truly apply to that data? Or is the ultimate challenge simply a matter of indefinite archival protection?
The law demands eternal retention. Security best practices demand timely, provable destruction. That profound balancing act, the conflict between legal liability and technical risk, that is the lifelong challenge of the asset security professional.
Think about the security systems you would need to guarantee the integrity and confidentiality of data for 50 years without relying on destruction. That's the real deep dive.
Something to chew on. Thank you for joining us on this deep dive into asset security. We'll see you next time.